I hope everyone has their thinking hats on, because now we're talking about magnetic fields. And the IB topics that we're going to hit is we're going to talk how moving charges cause these fields. We're going to draw these field patterns. And the IB doesn't state specifically that you have to do this, but it's recommended that you use some right-hand rules to figure out these field patterns. Now, it is true that moving charges, such as in wires, do give rise to magnetic fields, but you're often going to be asked to understand what's going on in things where maybe you don't know charges are moving in. For example, in a permanent bar magnet, you've got north lines, south lines. If you've ever done the thing where you sprinkle the iron filings on there, you'll see the filings line up as if they were magnetic field lines, and that's kind of cool. And what it looks like is if you have lines that fly off of here, these lines never cross, and where they are more concentrated, that shows that the magnetic force is stronger. Now those should not be crossing. I'm just not a very good drawer. And we draw arrows that show that they are going, oops, that's wrong, out of the north and into the south. If you have a compass, we have a little compass, we say that a compass, the point of it is a north pole. And you know that opposite poles attract. So if we define the tip of a compass as being a north pole, the tip of a compass will go towards the south and away from the north. And so this is the way that compasses would be pointing, always away from the north towards the south, and they line up along those field lines. Now, that seems fine, but if you've got the earth here, and let's say here is what we usually call the top of it, up here there's a guy with a beard, he's got a hat on, big red suit. This is where Santa would be. And we call this the North Pole. However, we know that compasses will point this way. But if we're defining the tip of a compass as a north pole, then it turns out that it must be a magnetic south pole at the top of the earth, which is a little crazy. But based on the fact that we're defining tips of compass as north poles, what we call the North Pole geographically is magnetically a south pole, and the field lines will look just the same as if the Earth were a giant bar magnet. The first right-hand rule that I think you want to learn is called the right-hand field around a single wire rule. It's not a very good name, so I like to call it instead the current hitchhiking rule. So the way this works, let's say that you've got a wire that's going straight up, and conventional current is flowing straight up. And so you make your thumb hitch a ride with the conventional current, even though electrons are going the other way. Don't worry about that. Conventional current, as we draw it, is going up, so your fingers would go up. And if you had a current flowing up, and sometimes as the IB likes to draw things, they like to say, pretend there's like a sheet of paper, and if you had to draw the field lines on this sheet of paper that was perpendicular to the wire, then you would get these circles. And if you sprinkled iron filings, you'd see these circles that are going around the paper, but they get farther apart. Oops, should be farther out, because the field gets weaker. But it is going in that direction that your fingers curl in. If it were going the other way, then it would curl the opposite direction. Another way you can think of this is, let's say you have a wire and you have current coming out of the page. It's coming straight at you. Then you make your thumb act like it's coming at your head, and if this were coming right at your head, your fingers would curl a certain way. And if you're using the right hand, then the field lines would be circular. And they're going to get more spread out. And opposite if the wire was going into the page. And current is into the page. Then your field, or your fingers, will curl the opposite direction. And it'll look just like the other one, except you would have to draw the lines as going the opposite way. That's the first right-hand rule. And the second right-hand rule is called the right-hand solenoid rule. Also not a very great name, but what is great is this drawing of a solenoid that I made. Take a look at this. Wow, that's a nice solenoid. You got your wires wrapped around, it's looking good. So let's say that we've got some electricity flowing through the wires. It's coming up and it's curving around through the solenoid. It's going to go down this way. And you're wondering, you know that this solenoid is going to make it a magnetic field that looks like a bar magnet, but because it's going to make an electromagnet. But which way is going to be north? To figure this out, you take your right hand and you make your fingers do whatever they need to curl with those wires. And whichever way your thumb is pointing, that is the North Pole. In this case, your fingers, if you're looking at the screen, should curl out of the screen towards you, putting your thumb of your right hand this way. And that makes this the North Pole and this the South Pole. And what you'll get is field lines that will go around like a bar magnet, just as you've seen before, not crossing. And we draw them coming out of the north. If you instead had electricity, here's the same solenoid, but you reverse the flow, and now electricity is coming out this way and down. You'll notice if you take your fingers, and if you're looking at the screen, you'll make them curl into the screen, and you'll find that your thumb in your right hand is pointing now this way. And this side is the North Pole, and you get the exact same field pattern, but in the opposite direction.